Okay, welcome back. Cambridge National Award Certificate in Systems Control and Engineering, R113, Electronic Principles. So we were talking about capacitors, and on the last video I'd set you a little challenge, but let's just have a little recap. So capacitors, polar component, it's got a positive leg and it's got a negative leg, it has to go the right way around. When connected to a battery, it picks up a charge and stores that charge, a bit like a mini battery. When it's connected in a circuit, the electrons then discharge through any components that are in the circuit, providing power for those. It happens very, very quickly, so we talked about the fact that it charges very, very quickly and it discharges very, very quickly. So here you'd see a bright flash and then the lamp would die off very quickly as the electrons sort of slowly finished part of the discharge. But we also mentioned that this charging and discharging can be controlled with resistors, and we're going to be going on to that in a few minutes. So the temptation is, when you see this sort of problem, is, well, you think to yourself, this is just like resistors, so I'm just going to go 2 add 2 is 5. And unfortunately you would be wrong. In series, resistors add up, but actually capacitors and resistors are different, and therefore they work differently. In this situation, when we're talking about parallel, you would have capacitor 1 plus capacitor 2 equals the capacitor total. So here you would have capacitor 1 is 2, and 3, so that would make 5 farads. Whereas in series, these actually operate very similar to resistors in parallel. So the equation for capacitance total in series, if you will, is 1 divided by 1 divided by capacitor 1, added to 1 divided by capacitor 2, and obviously that would continue. So in that situation we now have the capacitor total for series would be equal to 1 divided by 2 plus 1 divided by 3. So that's a half, so that's 0.5, that's a third, so it's 0.333 recurring, but I'm just going to say 0.3. So that would go to 1 divided by 0.8. So we would be looking at 1.25 farads. And again, similar to resistors, in this case it's smaller than the smallest capacitor. Again, these are likely to come up with the examination. You will get resistors in series and parallel. It's quite possible that you'll get capacitors in series and parallel as well. So you do need to be familiar with the fact that this goes with parallels. This goes with series and parallels add up, whereas in resistors it's effectively the opposite. So you must try and make sure that you sort those out. Going back to talking about charging and discharging capacitors brings us on to resistors and capacitors working together. And what we're looking at here is effectively a situation whereby we have a resistor and a capacitor, like so. We'll have volts, negative volts. Now I'm going to put, we'll put a voltage coming in here to complete the circuit to charge up the capacitor, and then we would connect the circuit coming out this way to discharge. And what we were talking about is that when you connect a source of electricity, you get this sort of steep climb and then this sort of gradual as it's filling up. It never quite gets full, and this is time constant t, and this would be the charge going up there. And the same when you complete the circuit and it discharges, so it would be quite rapid, fading off. Now what's interesting is you can add in a resistor to the situation and you get a formula, time, which is in seconds, is equal to the resistor times the capacitor. Okay, so you could have a resistor of 10 ohms, and you could have a capacitor of, which would be large, 1 farad, and then you would get, this would take 10 seconds. It would take 10 seconds to get fully or nearly fully charged, and it would take 10 seconds to completely discharge. So time is resistor times capacitor, 10 times 1 is 10, and that would be 10 seconds. That in itself seems simple enough, but capacitors rarely come in such a large size, and in fact it is more common for us to talk about millifarads, microfarads, and nanofarads. Got a bit far there. Nanofarads. Quite small. In fact, milli is times 10 to the minus 3. So 1 millifarad would actually be 0.001. So 10 to the minus 3. Microfarads is 10 to the minus 6, and nanofarads 10 to the minus 9. And we're very keen, in engineering we very much like this, minus 3, minus 6, minus 9. And we use this notation a lot, and we often have what we call prefixes, milli, micro, nano, and for greater numbers, numbers larger than 1, 10, we would go for kilo, mega, and giga. Okay, and we'll be talking about those a little bit later on as well. So, working out timing constants, you can end up with situations where you've got quite large capacitors, 100k, multiplied by quite small capacitors. And this is something that you need to be aware of and again practice. So let's have a look at this one in a bit more detail. Effectively 100k or 100 kilo ohms would be 100,000 ohms, and we will be multiplying that by the 100, but 10 to the minus 6. Okay, my way of working that out would be 1, 2, 3, 4, 5, 6. That's where the decimal point goes. There's a naught, there's a naught, there's a naught. So effectively, that's 0.123. Okay, so you've got 100,000 times 0.0001. We have a little blip or a little power failure there. So I think there's a little power failure there for a second. Let's go back to this. So we would effectively get 100 seconds. Like I was saying, resistors come in quite large numbers, capacitors definitely come in very small numbers, so you will need to become more familiar with engineering notation. Both very small numbers and very big numbers. Times 10 to the 3 would be kilo, like kilometers. 10 to the 6 would be mega, like a million, and times 10 to the 9 would be giga, like giant. But we'll do a separate video on these to cover both electronics and mechanical engineering. So let's have a look at sort of a circuit, give you a little bit of something to think about. I've got a power source, got a switch, and I've got a resistor, a capacitor. So I'm going to go for 10k here. I'm going to go for the 100 microfarads there. And then I'm going to put off here another switch. A resistor. Let's go for 100k there. And a lamp. And call this switch 1. And this switch 2. That could be R1. And that could be R2. And there's only one of these, so that would be C1. Okay, so give yourself a couple of minutes. We'll come back and have a look at this. So if you want to pause, what I want you to do is I want you to try and figure out what happens when you close switch 1. Okay, and then open it again. And what happens when you close switch 2 and then open it again. And in fact, actually, it would be useful to replace that with a switch symbol like so. This is a push to make switch. So you push it down to hold it down, then it would spring back open again. So again, switches is something that we will need to revise as part of the course at a later date. So you would press that down and hold it. What would happen? When you close this switch, what would happen? Give yourself a couple of minutes, see if you can do some calculations. Think about things that you know, Ohm's law, capacitors, timing constants, resistors, and see if you can figure out what would happen to the lamp after you've closed switch 1 for a bit, opened it, switch 2, and then opened it again. Okay, hopefully you've had a time to look at that then. So, if I close switch 1, I'm going to have this timing constant, if you will. I'm going to have time 1 is going to be equal to my 10k, 10,000, times my 100. Well, I worked that out here, didn't I? It was 0.0001. 1 farad, 10,000 ohms. So that's going to give me, it's going to take 10 seconds to fully charge. Okay, so I'd have to hold that closed for 10 seconds to get a full charge. The second timing constant would be when I leave that switch open. If I close that switch now, then the electrons are all stored on here, and the positives that are all stored on here. Well, the electrons are going to go through that lamp, through that resistor, so that's going to complete that circuit. So I now got a timing constant which is going to have a capacitor and a resistor, or resistor and a capacitor. So that's 100k. And I'm guessing you've already seen this. You're thinking, ah yes, but I do want to keep this reasonably simple to start off with, because I just want you to understand how it works. So we're going to effectively get, so the lamp would stay on for about 100 seconds, which is about a minute and 40 seconds, so a minute and a half. But remember, because it's not absolutely exact science, so that would be about a minute and a half as the lamp started to glow, and then it would slowly fade. So you could sort of draw a graph of that over 100 seconds. That would be 50. It would start off here, and then it would go sort of like that, discharging. And again here the graph for the charging, that would be 10 seconds, and sort of over that 10 seconds it would sort of be like that, charging up. And that is how we calculate resistor capacitor circuits as timing constants. And you'll actually see that timing constant used when we start talking about things like 555 chips.